Hello again, and this is our next lecture in ME6008. The microfluid in this lecture is looking at the effect of compressibility. And this is quite unusual in the sense that in liquids in fluid mechanics, we universally treat them as incompressible. But we know that liquids have similar densities to solids. You know, it's of order 1,000 kilograms per meters cubed. And in analysis of solids, we look at the influence of compressibility. And what we find with liquids is that they are, in fact, a little bit compressible. And usually that has no effect on the result of the fluid mechanics, so we neglect it. And our criteria for neglecting it is pretty much, if it's a liquid, we neglect it completely. And if it is a gas, and we know that gases have, you know, a density which is 1,000 times less than that of a typical liquid. So there is a lot of space between the molecules. When you apply any kind of reasonable pressure, you're able to push those closer together, so you're able to change the volume, and they become compressible. And even with gases, in a lot of fluid mechanics situations, we don't consider the compressibility of the gas. So typically, the criteria that we use would be the Mach number is less than 0.3. So it's really when Mach numbers become greater than 0.3 that we start to consider that the flow may be compressible. And most of the Navier-Stokes equations that you would see typically consider that the flow is incompressible. Now, when you get very, very, very small, we've seen from the previous section that the flow resistance becomes very, very high. And if we take, you know, a square channel, we know that the pressure drop is inversely proportional to the height of that to the power 4. So as we get smaller and smaller and smaller, the pressure drop gets really, really large. And what happens is that the pressure changes start to become appreciable. And this can introduce a capacitance effect into the response time of the fluid, because there is a bit of capacitance in there that the deformation of the fluid takes up that influences the pressure as it evolves as a function of time. So it becomes a transient effect. And that's what we're going to look at in this lecture. And we're essentially going to be concerned with pumping systems. So just before we do that, just note that the criteria for liquids, with liquids, is that we consider it if the pressure is going to be high enough, and that's the analysis we're going to do. When we're dealing with gases, and we haven't covered gases yet because gases are pretty unique when it comes to microfluidics. Even when the Mach number is less than 0.3, you can get compressibility effects with gases, particularly when you have high pressure ratios. Okay, so although your Mach number may be below 0.3, your pressure ratio cause may be sufficient to introduce compressibility effects. Okay, so there's your two kind of health warnings on this. Now, gases, as I said, we'll look at later. We're going to look at liquids in this example. So the first thing we're going to do is look at this kind of bulk modulus definition. It's essentially a 3D Young's modulus. So the bulk modulus is defined here. I'll just change it to the pen. So this is our definition of the bulk modulus. So minus V to PdV. And we have the negative on it because when the volume decreases, when a positive pressure is applied. Now that formulation here is in terms of pressures and volumes, and what we prefer to get is something in terms of pressure and density, which we have there. So we can use M equals rho V and take the differential of that, so dmdv. And mass is conserved, so dmdv has to be equal to 0. So that gives us this relationship here for density. So when we go back to our density, we want to change it into pressure and density. So we make our substitution change of variables, so dp d rho dv. And we substitute this out using this relationship here. So we end up with the result that the compressibility, the bulk modulus is equal to rho times dp d rho. And this is a result we use in a little while. It's a more convenient formulation of the bulk modulus. All right, so the scenario we're going to look at is that of a syringe pump, and these are what are typically used to deliver flow in micro. And one of the things you'll probably not recall about syringe pumps, and if you had something like a centrifugal pump, one of the key things with a centrifugal pump or an axial pump is that you must match it to your system. So if you're going to connect it to a piping system, it doesn't just deliver the max flow that it is set to. It depends what resistance it sees in the piping system. And the operating point is determined by the intersection of the pump curve and the system curve. Now with syringe pumps, they have a vertical characteristic. And what I'll do is just load up a blank page and try and sketch these out for you so I can show you what I mean. Right, so I swapped over to blank slide and I'll try to sketch out a pressure drop flow curve. Okay, and if we go for a system curve will have shape a bit like this. Okay, so it is made into two regions. One is linear, although it doesn't look particularly linear there, but essentially here is the F of U in that region, so linear. And here it's Q squared, so it's inertial. Okay, so this would be an inertial dominated region, this would be a viscous dominated region. And typically in electric systems, we're in this kind of linear pressure flow relationship, which we had from the previous section. Now, if I have a pump, we'll go for a pinky color. A centrifugal pump has a curve a bit like that. Okay, and this will be its max flow that it will deliver, and this is the max pressure rise that it will give. So this point here is determined by literally essentially dropping the pump in a reservoir. So there's no pressure up across it, and it delivers its max flow. Here it's giving maximum pressure rise, so there's no flow. So you've blocked off the inlet and the outlet, and it's just churning the fluid. And it gives you a maximum pressure rise between the inlet and the outlet. So it goes into service and it needs a system. See that our system curve here, so that is the resistance in our piping, our channels, and where that intersects with the pump curve, which is this one, P-U-M-P. This is our operating point. So if you change the system, so you reduce the flow rate, for example, you change the operating point. Okay. Now with a microfluidic system, because the pressure drops tend to be very, very large, what is done is, I'll just rescale that so we draw our axes again. So with pressure drop and flow. And again, our system curve will essentially be linear because we're down in the microfluidic region. And the pump curve has pretty vertical shape for a syringe pump. And this is typical of most positive displacement pumps. So essentially what it means is that no matter what resistance it sees, whether it sees a high pressure system or if we draw another system that is a low pressure system, sorry, I'll draw a high pressure one here. Again, you can see that the operating point is consistent. No matter what resistance we see in the system, it delivers the same flow rate. And this kind of squiggle up here is where it pushes back. That's where the pump is starting to fail. And this is a typical curve for most positive displacement pumps. So syringe pumps are in that category. So because we're dealing with high pressure systems, we tend to use syringe pumps. And again, the volumes are small. They're limited by the travel that they can do. So they have a fixed volume, as we can see inside here in the syringe. And that's what it displaces in, but usually that volume is quite large relative to the size of the system. So we're going to look at analysis of this. So we have our dimensions, and it's connected into our microsystem here. Now, usually we have a bit of tubing, but we're going to neglect that tubing. It's essentially considered to be part of the syringe. Okay. So this dimension D is characteristic of what's going on in the syringe. So we have a velocity in the syringe, which is UP, and at a certain instant, time greater than or equal to 0, the pump undergoes a step change. So this plunger here starts to push in and it displaces the fluid and pushes it through the system. Okay, so at t equals 0, the piston velocity suddenly becomes capital U. Okay. So because our syringe is large, the pressure gradient must be small. So our system pressure drop is dominated by the microchannel. That's a feature. We've seen this in the experimental section, where you're measuring pressure in inlet and outlet, and we saw examples of the setup over in Toulouse, for example, where the actual pressure gauges are located a bit of a distance away from the microsystem, but they're connected by relatively large tubing compared to the size of the microsystem, so that the pressure drop is already dominated by the microsystem. And you're essentially measuring the pressure. Okay, so a pretty reasonable assumption. So what we have therefore is the continuity equation is applied, but now it's transient. Okay, and we've included the density term inside here because we're including compressibility effects. Okay, so d rho dt plus d rho up dx equals 0. So that's our continuity equation. Now we're just doing this in one spatial dimension. Okay, just in the flow direction. So if we integrate that expression, we end up with this expression here.
You are currently the only person in this conference.
Audio, hopefully it's back again. I'll have to check that in the recording. We want to change our variable from density into pressure. We also want to work out this constant of integration here, C1. So these are boundary conditions to get that. Okay, so we get C1 is equal to this thing. And we make the substitution that we had earlier in for density. Okay, so we're using that expression that we drew back here. So that gives us UP is equal to minus 1 over k dp dt, x minus ut plus u. Okay, so now what we want to do is we want to lose this UP. We want to express UP in terms of pressure so that we have an equation that really just has pressure as the variable. We have time here, that's fine. That's one of our, it's a transient solution that we're after, and this is a boundary condition that we have in there. So what we're going to do is we're going to look at where the pump connects onto the micro device. And we're going to look at the continuity there of the flow. So most of the syringe is the velocity times the area. Okay. And what is going into the microsystem is the velocity in the channel, the microchannel, times the area. In this case, we've got a rectangular cross-section of width W and height H and length L. Okay, so pi d squared over 4, sorry, I should put that with that, is the area of the syringe, and WH is the area of the microchannel that we've connected it onto. Okay, so that allows us to express UP here in terms of the channel. So we have the hydraulic resistance to link the channel velocity to a pressure drop in the channel. Okay, so that's what we do next. We're using our flow resistance expressions that we had before, and we're now linking the velocity in the channel to the pressure drop. So the flow in the channel is linear with the pressure drop. So we end up with this expression here. Now this pressure drop, we're going to reference it to 0, okay, at the outlet of the channel. And that lets us replace the delta P with P. So when we combine all this and make the substitution in, what we end up with is this expression here. Now we can see that now we've got everything in terms with pressure as a variable. And what we want now is to solve the function of pressure as a function of time. Now, this equation, if we look at it here, it's got dp dt, it's got a p, it's got a constant. So it's a pretty, if we can get this thing to be 0 or very, very small. And to get this thing to be small, physically what it means is the piston is far away from the end of the syringe. Okay, so what it means is that the piston is a good bit away from the outlet of the syringe. Now again, if you're going to run a test, there's not much point to run the test if your syringe is located here, the plunger, because you've already got a small amount of travel to deliver a bit of flow. So you usually run tests where your syringe has a decent bit of volume in it, so you've got a good runtime in it. So this term is small ut over L when the piston is far from the end of the syringe. So it's not traumatic to meet that requirement. It's pretty straightforward. And now that equation simplifies down into dp dt plus p times this is equal to uk over L. And this is a pretty straightforward in fact. Now I have a slide 2 on integrating factors that just explain what they are, because you may have forgotten from your maths. So again, they're quite useful. I'm not going to go through them here. It's up to you to understand things. But essentially, if you look at the use of integrating factors in solutions, this is the form of our equation, where we have dp dt plus p over tau, where tau is this thing. Okay, and the solution, again, we can work. Essentially, what we have is that our solution comes out to be this form. The steady state value controlled by a rise time, which is linked to tau. So tau here is the characteristic time for our system. Now, to kind of make sense of that, what it means is that, and the way to think about this is really in terms of an engineer. When we go and just clear this, if we look at this equation here, once we know that that's gone, so that's out of it, that ut over L. Once we see this, we look at the term inside the to the pressure term, the single pressure variable, and that is 1 over tau. And that's our time constant. So if I want to know how long it takes to get to steady state, anywhere from 3 to 5 time constants is appropriate. Okay, so at that stage, I think at 3 time constants is about 99%. At 5 it's 99.999%. So you're pretty much there with 5 time constants, and you're as good as there with 3. So you simply evaluate this and multiply it by 3, 4, or 5, and that's pretty much how long it's going to take your system to reach steady state. So you don't actually need to solve this equation. We just look at this term here, and we're able to extract the time constant from it. So again, the mathematics of that is covered through this, and the solution here as we final solution here. Okay, but in essence, all you need to do is look at this thing, the time constant, and calculate that and multiply it by 3, and you have an idea then as to how long it takes for your system to reach steady state. So again, the physics of what is going on is that the pressure drop across the microsystem is so large that it causes back pressure combined with this causes a delay in the response of the system to establishing the pressure drop. So how long does it take? So if we do an example here, this is data taken from Patrick Tabeline's book that has a 1.4 micron microtube, and he's changed the flow rate from 10 to 3 nanoliters per minute. Okay, and you can see that he gets this decay in pressure. So it goes from 1.6 bar down towards 1.2 or thereabouts. Okay, but look at the time axis. It's taking really happen. Okay, so he comes in, he changes the setting on his pump. A day later, the system has stabilized. Okay, now the size here of this 1.4 microns is tiny. Like usually we're up at about 100 microns. And in a 100 microns channel, if you do the calculation, do the comparison one, it ends up being a very, very small, practically instantaneous time. So this effect becomes manifest when we have very, very small channels. And again, we can see, if we look at the form of this, we can see the factors that increase it. So increasing the length of your system, okay, gives you much more fluid, much higher pressure of fluid. If you change the dimensions, again, make them smaller. So h cubed here. So it starts to become very, very long. If you go very, very small here, it's quite long. In essence, what we're saying is that if the change in volume in the fluid in the syringe due to the compressibility of the fluid is of similar magnitude to the device, in essence, and the physics that is going on in this. Now, in this analysis, we've only considered the fact that the syringe is rigid, so it's got structural wall. We're only looking at the deformation of the fluid. Very often when you get to these high pressures and you're using kind of flexible tubing, the walls are deformable, and now you're into a fluid structure analysis, and that's quite complicated. And you need to do a coupled analysis, typically using computational fluid dynamics and finite element methods. So that becomes quite tricky to do. So you will get additional capacitance due to that will extend beyond those. So just be careful that this analysis here is only applicable for rigid systems, where only the fluid contributing to the compressibility effects. So in summary, what we're having is that the syringe pump is using a piston arrangement, which is requiring a significant force to be applied to a large volume of fluid, compressing the fluid and increasing internal pressure significantly. And if that volume or the magnitude as you end up with a problem. A way around this, well, one way is to use a constant pressure source. Okay, so you don't have those pressure transients, and that's not always feasible to do. Another solution is, well, operate the syringe pump under withdraw. So instead of trying to ram the fluid through the microsystem, and the system is trying to resist it, just pull it back. So the system will flow out, and you don't have these. It causes its own challenges, because what happens then is that your pressure inside the system becomes subatmospheric, and air then can get in very, very easily. And remember that gas molecules are quite mobile; they're very, very small, so it's very so very often getting around that's issue of compressibility. So, an issue. Okay, so to summarize, and if you look at past exam papers, or the kind of questions that have been asked, our scenario is, in our scenario, we were considering a rectangular channel. Okay, so W and H. Actually, H there. And what I did. Be H when so with so if you look at the circular ones, example triangular ones, and things like that, and what happens there is that when you get to this stage, this continuity balance changes. Okay, so the area here, WH is for a rectangular channel. If you had a square, it would be H squared plus a tube by over 4. If it was triangular, half the base by the perpendicular height, etc. Okay, so whatever the area is. And you may need to go back to the previous slides resistance values. So depending on their shape here, you can see the hydraulic resistance values here. Enable you to link the drop to the flow rate and see what's so you can see the resistance values being used here. Okay. So again, the expectation is you've seen this in previous exam papers, is to be able to perform this but with different channels and to be able to drive the time constant for that. Once you spot it, you understand that it's got this to be just one of. When you look at this, and this is 1 over tau, and that's so take 3 times that value, calculate tau, and multiply by 3, 4, or 5, whatever you fancy, and that gives you how long you need to wait for the system to stabilize. Okay, I've covered quite a bit of stuff there. So with that, if you have any particular questions on it, just come back to me with it. You might need to listen to this a few times. You might need to brush up a bit on your integrating factors to understand that. The take-home method to get to this value of tau, you're basing your solution off, that you're interested in what that time constant is. Okay, I hope that's been useful for you. And as I said, if you have any questions, just drop me an email and I'll try to get back to you as quick as I can. Thank you for listening, and see you again soon. Bye-bye.